This is our first discussion about heat and energy in chemical reactions. And as we know, heat and energy is something that's very important because every chemical reaction is either going to cause energy to be released or absorbed, and that's something we're going to talk about in this discussion. Now here's just a very simple example of a chemical reaction. We have H2 plus F2 yields 2HF. Now if we think about what's happening on the molecular scale, well, you have to have a molecule of H2. I'm going to make a little drawing that helps us to maybe understand or visualize what that looks like. This is just a model to help us visualize an H2 molecule. And then over here we have an F2 molecule. It's got 2 fluorine atoms in it. Well, these molecules are moving around in space, and in order for them to react and make 2 molecules of HF, they have to collide in such a way that they're able to do that. Now, they have to have 2 requirements met. First of all, these 2 molecules have to collide with sufficient energy. And so in other words, they have to collide with enough force. It's like if you have 2 Legos, in order for them to be stuck together, you have to push them together with a certain amount of force. And so if you don't have enough force, well, those 2 molecules are just not going to react. They're not going to stick together. Well, the second requirement for these molecules to react with each other is that they react in the correct orientation. So what that means is they have to hit in this direction. They have to actually hit like this, straight on like that. If they hit, say, one on top of the other, that's not going to work. They have to hit in the right orientation. It's like with 2 Legos. You can't take 2 Legos and expect them to stick together if you push the 2 raised sides together. It doesn't work that way. They have to be pushed together in the right direction. And the same thing with these 2 molecules. In order for these 2 to react, you have to have that requirement met. Now, in the case of this, we have, as you can see up here, we have a molecule. It looks like it's H2F2 that has been produced. If these molecules collide with enough energy and the correct orientation, we have H2F2. Now that's not what we're trying to make. What we're trying to make are 2 molecules of HF. And so what has to happen is we have to be able to take 2 bonds and erase that bond right there, and that bond has to break in order for us to be able to make, as you can see, 2 molecules of HF. This is the process that we go through in order to make that molecule or those 2 molecules in the products. So what was this H2F2 all about? Well, that was a very temporary transition state. That's something we call an activated complex. And activated complexes are basically very high energy, unstable compounds. And they're formed after the reactant phase, but before the product phase. Now sometimes an activated complex is called a transition state. That's a phrase you'll hear sometimes. But in this class, we're going to call this an activated complex. That's a common term for this. It doesn't last very long, and it's what you make when all these bonds stick together and right before the old bonds break in order to make your new products. Now let's take the energy in this reaction, and let's just, well, it doesn't have to be this reaction, it could be just any reaction, and let's plot it on a graph. And so in this case, we're going to take, as you can see here, the reaction pathway, which is basically just a way of talking about time, and we're going to plot that on the x-axis. So reaction pathway is basically time as it proceeds, and the energy, the potential energy of the molecules involved in this reaction are plotted on the y-axis. And as you can see here, we start at a certain amount of energy, and then once the reaction starts, it goes up and up and up until it hits a peak. And then, as you can see, it starts to drop. And it drops and drops, and it keeps dropping. It drops even below where we started. And then when the reaction is complete, we have this new amount of energy. And we're going to plot all these energy values on our diagram here. Well, the first thing that's hopefully pretty obvious to you is this amount of energy right here, the amount of energy that we have at the beginning. And we don't have a whole lot of energy here, or a whole lot of room, I should say. So I'm going to make a little A, and I'm going to label that over on the other side of the slide here. And A, we're going to call that the energy of the reactants. I hope that makes sense, because that's what you have at the beginning of the reaction. We have reactants at the beginning. And so that makes sense, that's the energy of the reactants over here on the left. Now, if that's the case, then what do you think we'd call this amount of energy over here at the end? Well, I hope you said energy of the products, because that's what you have at the end of a reaction. I'm going to label that as B, and we're going to call that energy of the products. And then we have this very high energy, this thing here in the middle that's at that peak. Now, let's label that. Kind of hard to draw a straight line on here. But you might remember that we had this thing on the last slide that we said is it's high energy, and it's after reactants, and it's before products. And what was that called? It's called the activated complex. And so that amount of energy right there is called energy of the activated complex. As you can see, that activated complex does not last very long. It only exists for that very brief point right up here at the peak. Not very long at all, whereas the reactants exist for a pretty long time, and the products last for a long time as well. Now, we have another amount on here. It's the distance from the starting point up to the peak. And it looks like that's the amount of energy that's required to get the reaction started. Because if we can get to that point, like right there, then this reaction is just spontaneously going to go all the way down here, kind of roll downhill, as it were, down to the product side. And that energy that's required to get the reaction started, I'm going to label that as D over here, it's called the activation energy. And in chemistry, sometimes activation energy is abbreviated as E sub A. E sub A, that's activation energy's abbreviation. And it's just the amount of energy that's required. We're going to say the energy that's required to start a reaction. And if you can get the activation energy, and there's a pretty good chance you're going to be able to make the products. To start a reaction. I'm going to abbreviate that RXN for reaction. Now, we have one other feature on this graph that I want you to be aware of, and that's the difference between the starting point and the ending point. And so I'm going to label that as E, and that is called the change in enthalpy. Enthalpy is a fancy word for heat. It's a certain type of heat, though. It's the heat that's locked up in chemical bonds, as opposed to, say, friction type of heat that you get when you rub your hands together. Change in enthalpy, and we're going to label that as delta H, because change, of course, is delta, and then enthalpy, we have the H there for that. And so this is just the difference between the starting point and the ending point. Now this tells us how much heat is given off in this reaction. And as you can see, it looks like however amount E is, that's the amount that's given off. Because we started with this amount of energy on the left side, and we end up with that amount of energy on the right side. So at some point, we lost some energy. And where did that energy get lost to? Well, to the surroundings. And so when heat is lost to the surroundings, we call this an exothermic reaction. So this type of graph you see right here is an exothermic reaction. Now, that's pretty typical. Most reactions, as it turns out, are exothermic. However, some reactions are not. And let me show you another graph. This is very similar, except look at that. You see how it's basically flipped around. This is where we start out with a certain amount of energy here, and we end up with more energy at the end. And so it looks like we've actually gained energy. And when when the molecules involved in the reaction gain energy, that's called endothermic. And so this is also an energy profile, but this would be for a different reaction. It's endothermic. It's absorbing energy from the surroundings. It absorbs heat. And so if you were to put your hand next to an exothermic reaction, it would feel hot to the touch because it's giving off heat. Endothermic reactions, if you put your hand next to that, it would feel cold because it's absorbing heat. It would feel cold to you. And of course, everything else is the same on here. It's just the delta H looks like it's gaining energy. Your change in enthalpy. Now let's talk about one other thing, and that is ways to speed up a chemical reaction. And so sometimes in chemistry you want to speed up, occasionally slow down a reaction. So we're going to talk about ways to affect the rate. Now the first one is to add a catalyst. Now when I say a catalyst, we're talking about, as you may have already known, something that speeds up a reaction, and it does that without being consumed. Now there are several chemical demonstrations that I can show you, and at some point in the classroom I'd like to show you one. And this is what happens when you add a catalyst. It basically lowers the activation energy of a reaction. So if I'm going to add a catalyst, let me just flip back to the other slide here. If this is a normal uncatalyzed reaction, well, I can add a catalyst, and the reaction is going to look like this. It's going to lower that hill so that more molecules are able to achieve that amount of energy. So that red line is the catalyzed reaction. Since the hill is lower, it's going to go faster. So activation energy is lower. It doesn't change your reactants or your products or your delta H. It's just the activation energy. So that's a catalyst. The second way to speed up a reaction is to increase the temperature of a reaction. And maybe you've seen this if you've ever done any cooking at home. You know that if you ever try to take a frozen pizza and put that into the oven, well, it's going to cook at a certain rate. What if you only heat up the pizza to 200 degrees Fahrenheit? Well, that's a pretty low temperature. It's going to take maybe an hour or two to cook the pizza at that temperature. So most of the time, we like to put the pizza at about 400 or 450 degrees Fahrenheit. And when you do that, the pizza is going to cook pretty quickly, in about 15 or 20 minutes. If you go to New York City, they're going to cook a New York-style pizza in an oven that's between 800 and 1,000 degrees, and that pizza will cook in 4 minutes. And so by raising the temperature, you raise the rate of the reaction. And that's because more molecules are colliding. The molecules moving faster, and when they collide with more force. Normally, just a little rule of thumb we talk about in chemistry is that on average, if you raise the temperature by just 10 degrees Celsius, just 10 degrees, that's going to double the rate. Now, that's not for every reaction, that's just a rule of thumb. Now, a third way to speed up a reaction is to increase the concentration. And so, when you do that, particles in the solution or in the compound are closer to each other, and so they collide more often. It's perhaps you've observed this before when you take a very dilute acid, like let's say orange juice, and you spill that on your hand. Well, that's not going to hurt you very much because it's a very dilute acid. You don't have a whole lot of acid molecules there unless you just leave it on your hand for, I guess, hours and hours. On the other hand, if you spill concentrated acid on your skin, something that we might use in the laboratory, well, that's going to react with your skin very quickly, and so that can hurt you very fast. And so the higher the concentration, the faster that something can react. Now, the fourth way to speed up a reaction is to decrease the particle size. And so maybe you've tried this if you have a log or a piece of wood. You know that if you take a log and you burn that in a fireplace, it might take a couple of hours to burn that log. If you take that log and you cut it down to the size of wood chips, it's going to burn a lot faster. If you take those chips and pulverize them down to sawdust, well, it's going to burn almost instantly, isn't it? And this happens because when particles are smaller, you have more of a surface area. And so more of the reactant is exposed. It's able to react with the other reactant. So you have what's called more active sites. So more active sites, when you decrease the particle size, have a greater surface area. Now, if you're not careful, this can cause disaster. Here's an example of this. Back in 2008, there was a sugar refinery in Port Wentworth, Georgia, and because of all the dust that was in the air, basically the entire sugar refinery exploded and killed several people. And so this was a tragedy. This is an accident, an industrial accident that is used even today to help people see the dangers of having very small particles in the air. Even something that's normally not considered to be very dangerous, like sugar, all of a sudden becomes explosive if the molecules, or I should say the particles, become very small. And so once again, the 4 ways to speed up a reaction: add a catalyst, increase the temperature, increase the concentration. Sometimes if you're talking about gases, we'd say increase the pressure, basically the same thing, or decrease the particle size. And so that's our introductory discussion for heat and energy in